Hi everyone, welcome to Physics 2 Lab 2 Magnetic Field of a Bar Magnet. I'm Xining. The contents of this lab include introduction, key physics principles, experiment, and discussions. The goal of this lab is to find the magnetic field of a bar magnet. By applying the Beal-Savart law and using the Python language, we can get the measured and simulated off-axis magnetic field of a bar magnet. Here are the preview results of this lab. Magnetic field increases while the distance decreases. The measured results of 45 degrees off-axis magnetic field is 7.06291 e-5 teslas, while the simulated result is 7.99281 e-5 teslas. The main physics principle we'll use in this lab is Beal-Savart law. The magnetic field of a point charge is equal to magnetic constant times the cross product of QV and R hat over R squared. The magnetic field of a current wire is also given as the magnetic constant times the cross product of the current times change of length and R hat over R squared. The current here is always the conventional current. The other concept introduced is called the magnetic dipole moment. It's similar to the electric dipole moment, while the equations are different. The magnetic dipole moment is given as the current times the area. A loop current, for example, the magnetic dipole moment is given as the current times pi squared. As a bar magnet is also a dipole magnet, so the following are the basic properties of a bar magnet. The direction of the magnetic dipole of a bar magnet points from its south pole to north pole, and the following equations are the magnitude of the magnetic field of the bar magnet's on and off axis. We'll use these two equations in the measurements and coding part. We can summarize the distance dependence relation by B bar equals K times R to the N, while we can get the N and K after the measurements. The K here is a combination of constants and parameters such as magnetic moment. In the coding part, to calculate the magnetic field of a 45-degree off-axis bar magnet, we'll use this equation. The things needed for the measured part of this lab is a bar magnet and the magnetometer on our phone. As mentioned before, the magnetic dipole moment of the bar magnet is from south pole to north pole, and the magnetic field is shown below. The system is the magnetometer, and the surroundings are the bar magnet and the Earth. Here are the measured results of different x component of the magnetic field for 5 distances. As we can see, the longer the distance, the smaller the magnetic field. When the magnetometer is relatively far away from the bar magnet, the magnetic field is nearly zero. We plotted the results on the previous slide and got the regression line. By applying logarithm, B bar equals K times R to the N can be transformed into ln B equals ln K plus N times ln R, which is the regression line shown on the right. So we can calculate for K and N. K equals 7.84672 e-7 and N equals negative 2.9732. By plugging the K back to our equations for off-axis magnetic field, we can solve for mu, which is 3.92336, and we'll need this number for the coding part. The result of this part also includes the B net of the bar magnet after correcting the Y component of B net because of Earth's magnetic field. In Atlanta, Earth's magnetic field is roughly 48.6 mu Tesla. So by subtracting in the Y direction that we get, our average B net result is 7.06291 e-5 Teslas on the lower right corner here. Next, move on to the coding part. We plug the mu from the measurements and define the B bar function by using the formula that I introduced earlier. On the right-hand side, I define the parallel and perp axis as well as the arrows at the different locations on the axis. Last but not least, I visualize in the magnetic field values for 45 degrees off-axis. On the right are the arrows and the results. As we can see, the magnitude of the 45-degree off-axis magnetic field can be calculated, and it is 7.99281 e-5 t. Notice that our measured magnetic field is smaller than the simulated result, so there could be 2 sources of possible errors while experimenting. First is the measurement errors including magnetometer not calibrated correctly, the error while measuring distance and the length and location of the cell phone while affecting the accuracy of results. The second possible error is that I did this lab indoor, which could cause other sources of magnetic field affecting the results. What if we don't orient the setup to compensate for magnetic north? This will cause x and y component of the result to change since magnetic north contribute to the x and y component for an intermediate angle. If the experiment is redone by using two identical bar magnets, then the magnetic field will be stronger, but overall it's still a bigger bar magnet, so the direction wouldn't change. That's the end of the presentation. Thanks for listening.